Today, we're diving into one of the most fundamental and, honestly, just mind-blowing ideas in all of science. I mean, really think about that for a second. Everything you can see and touch, everything you can imagine. How can all of that incredible variety come from such a tiny set of building blocks? It sounds totally impossible, right? Well, that's exactly what we're going to unpack in this explainer. Just look around you. The world is filled with this amazing diversity of stuff, what scientists call matter. You've got the unbelievably complex biology of a hatching ostrich, and you have the invisible air we're all breathing right now. And it's all built from the same basic parts, following a set of rules that are, you'll see, surprisingly simple. So to make sense of all this, let's use an analogy that really helps. Let's think of all matter as if it's written in a special language. And just like any language, this one has to start with an alphabet. So, the most basic unit, the absolute foundation of literally everything, is the atom. And get this, there are only about 100 different kinds of atoms in the whole known universe. These are the letters of our chemical alphabet. That's it. Now, when you have a substance that's made of only one kind of atom, say a chunk of pure gold or a tank full of pure helium, that's what we call an element. Think of an element as just a single letter, like A or B, just repeated over and over and over. It's matter in its simplest, purest form. But here, this is where things get really interesting. When these different atomic letters are chemically joined or bonded together, they form something new called a chemical compound. And this is how we start building all the complexity in the universe. And this diagram just lays it out so clearly. On one side, you've got those simple, identical atoms. That's our element. But on the other, you see where different kinds of atoms have linked up, forming something totally new. That right there is the key difference between an element and a compound. All right, so we've got our letters, the atoms. Now, how do we actually combine them to form chemical words?
Well, the word in our chemical language is called a molecule. A molecule is the smallest possible piece of a substance that has at least two atoms chemically stuck together. This is our fundamental unit for building pretty much everything. And molecules can be formed in two basic ways. You can either stick atoms of the same element together, or you can stick atoms of different elements together. Simple as that. Here's a perfect example of that first way. You can see how two individual hydrogen atoms can bond to form a single molecule of hydrogen gas. The oxygen we breathe is the same idea. It's just two oxygen atoms bonded together. And here's that second way, which is way more common. You take one atom of carbon, you bond it with two atoms of oxygen, and boom, you get a molecule of carbon dioxide. A completely new substance, a compound, created from its basic parts. But what does it really mean for atoms to be chemically bound? Is it just like, I don't know, mixing salt and pepper together? Not even close. Let's look at a quick experiment to see the huge difference between a simple mix and a true chemical compound. So first we take some iron filings and some sulfur powder and we just stir them up. This is just a mixture. And notice, if you bring a magnet nearby, it pulls the iron right out. Why? Because the iron is still iron and the sulfur is still sulfur. No new word has been written. The letters are just kind of hanging out next to each other. Okay, but now watch this. When we add energy, we heat the mixture up. You can see it start to glow like crazy right there in the test tube. That's a chemical reaction happening. The atoms of iron and sulfur are rearranging and forming powerful new bonds. And look at what we're left with. This gray, brittle stuff is iron sulfide. And here's the magic trick. The magnet has zero effect on it. The iron has been totally transformed. It's now part of a brand new substance with its own unique properties. We've written a completely new chemical word. So, with millions of possible compounds or words out there, how do scientists all over the world talk about them without getting hopelessly confused? Well, they needed a universal system. They needed a chemical grammar. Just imagine trying to do science if every country used different names and symbols for something as simple as water. It would be total chaos. For chemistry to move forward, it absolutely needed a simple, shared system that everyone could read and write. And the person who cracked this problem was a Swedish chemist named Jöns Jakob Berzelius. Back in 1813, he had this brilliantly simple idea. Let's just give each element a one or two letter symbol based on its name. This one move is basically the foundation of modern chemical language. And this is the exact system we still use today. Hydrogen is H, carbon is C,
Oxygen is O. Now, a scientist in Brazil can write H2O, and a scientist in Japan knows that means exactly 2 hydrogen atoms bonded to 1 oxygen atom. It's the perfect universal grammar for our chemical alphabet. So, let's zoom back out one last time and put this all together. We have our letters, atoms. We have our words, molecules, and we have our grammar, chemical symbols. How does all that build? Well, everything. The crucial point is this. Every single substance you can think of starts out as either a pure element, like a piece of aluminum foil, or a pure compound, like a grain of sugar. These are the fundamental building blocks of our entire world. And this flowchart, it just sums up the whole story perfectly. All matter is either a pure substance, which means it's an element or a compound, or it's a mixture of those things. From just over 100 different types of atoms, nature creates this incredible library of substances, which then get all mixed together to create the infinite variety we see all around us. It's really an amazing thought, the entire vast library of the universe, written with an alphabet of just about 100 letters. It really makes you wonder, doesn't it? What other huge, complex systems, in biology, in technology, maybe even in our own societies, are also built on a foundation of elegant, simple rules, just waiting for us to discover them?